Hi everyone, in this video we'll talk about waves, types and properties of waves. We'll describe longitudinal and transverse waves in ropes, springs, and water where appropriate. State the meaning of amplitude, frequency, wavelength, and period of a wave. Recall that waves transfer energy and information without transferring matter. Recall and use the relationship between the speed, frequency, and wavelength of a wave. Wave speed equals frequency multiplied by wavelength. V equals F times lambda. Use the relationship between frequency and time period. Frequency equals 1 over time period. Describe wave properties, how wave can undergo reflection at a plane surface, refraction due to a change of speed, diffraction through a narrow gap. What are waves? Waves are disturbances that propagate or move energy through an empty space or through medium. Medium means particles such as atoms and molecules. Waves transfer energy without transferring matter. Look at the figure. We have two shapes here, wave pulse and wave train. We have one pulse to move and train, which are continuous waves. A wave in the sea is a disturbance in molecules of water going up and down. The medium here is liquid, which is water. What are the types of waves? We have two different types of waves, mechanical waves and electromagnetic waves. Mechanical waves need medium to propagate, while electromagnetic waves travel through vacuum, no medium to travel. The example for mechanical waves is vibration of solid particles, vibration in liquid particles or gas particles, while in electromagnetic waves, we have vibrating of electrical and magnetic field perpendicular to each other. Look at the figure. Mechanical waves here, we have the first type is longitudinal waves. We must have medium, solid, liquid, or gas. Electromagnetic waves, which are electrical field and magnetic field to travel like this. They are perpendicular to each other. Here we have shape of mechanical and electromagnetic waves, which is transverse, and the other shape for longitudinal, which is mechanical wave only. To get a mechanical wave, we require a vibrating source, medium that carries a vibration, disturbance transmitted from the source to the medium. Wave properties. We have transverse waves and longitudinal waves. Transverse waves, as you see, the particles are moving up and down perpendicular to the propagation direction. And the other shape is longitudinal waves, where the particles of medium vibrate along or parallel to the direction of propagation. Here we have transverse waves composed of crest, which is the positive peak, and trough, which is the negative one. The equilibrium position of any wave is the middle point where the vibrations occur around. Also, we have something called wavelength. Its symbol is lambda, inverted letter Y. Lambda, or wavelength, is the disturbance from the equilibrium position to the crest, then to the trough, and back to the equilibrium position as standard. Transverse waves, lambda, measurement can be measured from two successive crests or two successive troughs, or from 2 points or 2 particles in phase. Both measurements will be the same. We have an example for the transverse waves, which is secondary seismic waves, which are found in earthquakes. The other type is longitudinal waves. Here, longitudinal waves vibrate parallel to the movement of energy in a wave. The particles here of a longitudinal mechanical waves will vibrate back and forth on the same plane as motion of energy transfer. Longitudinal waves are composed of rarefactions and compressions. As longitudinal waves propagate, they have parts of compressions where the particles are close to each other. We call it high pressure region, and rarefactions where the particles are further apart or low pressure region. Also, seismic waves is acoustic energy that travels through a planetary body. They are caused by the sudden movement of materials within the Earth, such as slip along a fault during the earthquakes, volcanoes, and explosion or landslides. Now we have a question. What do all waves transfer? The answer is energy. The second question is, what do waves not transfer? It's medium or the particles. Medium or particles return to their original position in mechanical waves, and in electromagnetic waves, medium is not necessary at all. Here we have something called amplitude. Amplitude is the maximum displacement away from equilibrium position or away from rest position. It's measured from the middle to a peak or a trough. The symbol of amplitude is A, and it's measured in centimeter or maybe in meters, where the velocity at one point is maximum here and is minimum at the other point here. So here we have maximum measurement and here we have zero measurement. Look at the longitudinal waves. It's composed of compressions and rarefactions, and they are moving parallel to the propagation direction, where the particles here close to each other is compression and further apart it is rarefaction. Here, to align between transverse waves and longitudinal waves, we have CC. What does it mean? C refers to crest in the transverse waves, and C refers to compression in the longitudinal waves. So, crests in transverse are equivalent to compressions in longitudinal. On the other hand, we can say rarefaction in the longitudinal waves is equivalent to the trough in the transverse wave. Here we have the wavelength. It's the distance between two crests or two troughs or 2 points in the same phase, like this. And the example is water or string, where the particles are moving up and down perpendicular to the propagation direction to form crests and troughs. In longitudinal waves, we have an example like sound or the movement in springs, where the particles compress and then move further apart, which are refractions. The wavelengths in this distance between successive centers of compressions or successive centers of rarefactions. To get the wavelength in this shape, we have to find what is the equivalent to A, or what is the suitable point to make one complete wavelength. It's E. So the wavelength lambda here is the distance from A to E. And the wavelength in general is the distance divided by number of waves. This is the wavelength from A to E, where the distance from A to E is considered as one complete wavelength. Look at this figure and try to match the highlighted letter to one which is exactly one wavelength away from it. Suppose we have D. Which letter here is matching? Look, D. It's P. Which letter matches J? It's V. Which letter matches B to make one complete wavelength? It's N. Now we'll talk about frequency. Frequency is nu or F. Okay, it is the number of waves over time must be measured in seconds. The symbol of frequency here is F, and the measuring unit is hertz or second to the power of -1. It's the opposite of periodic time. Look at this figure. We have movement of wave energy from one point to another. So it takes time about 4 seconds to make one complete cycle or one complete wave. So the periodic time here is 4 seconds. To get the frequency, the number of waves is 1, and the time taken is 4. So the frequency is 1/4, as you see. Okay? And to get the periodic time, we have to reverse the frequency 1/f. Look at this figure and look at the second timer here. Count the number of complete vibrations in 10 seconds and then work out the frequency of this wave. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the frequency is 1 hertz. Why? Because the number of waves here is 10 and the time taken on the timer here also is 10. So it's 1 hertz. Because the frequency number of waves over time, 10/10 equals 1. Look at the second one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So one complete wave takes 14 seconds. So we have another one here. It's much slower. And the frequency here is 0.5. So all in all, we have to know the number of waves done by the vibrating object in 1 second. This is a steady heartbeat. And we have here turbulence. So Rana has heart attack. And in this case, this one is dead man because there is no heartbeats. Wave speed. I mean waves math. We have velocity, frequency, and lambda, which is wavelength. Velocity is measured in meter per second. Frequency is measured in hertz. wavelength is measured in meter. To find V equals F multiplied by lambda. To find anything from this triangle, the factor you need, you have to cover it. If you want to find frequency, so cover the frequency, so the answer will be velocity over lambda. Consequently, lambda equals, yes, V over F. Calculating the speed of wave. As I told you, V equals lambda multiplied by F. In general, velocity equals distance divided by time. Okay? When a wave is treated like an object traveling a distance in a time, okay, V equals X over T. Okay? Notice in the picture that the wave travels 3 meters in a total of 2 seconds. The resulting velocity using V equals X over T is 1.5 meters per second. Look here, we have the distance is 3 meters and the time is 2, so it will be 3 divided by 2, okay? And the answer is 1.5 meter per second. From this figure, V equals lambda multiplied by F. Lambda equals 3 meters, which is the distance from one crest to the next one. And if we count the number of waves as 2 waves per second, so the velocity will be, yes, 3 multiplied by 2, and the answer will be 6. Now, let's talk about wavefronts. Look at this picture. We have a spherical dipper here work as a source of wave, which is moving up and down by a motor, okay, which produces concentric circles. All these circles are called wavefronts. And here, the blue transverse waves, this is the shape of waves, and these lines indicate the direction of waves. Any line or surface over which all the vibrating particles are in the same phase, I mean they have the same speed and at equal distance from their source. In this transverse wave, wavefronts are normally lines joining all the peaks at equal distance from their source. The distance between two circles, between two successive wavefronts, between two successive curves here equals wavelength, lambda. The direction of travel of wave is always perpendicular to its wavefronts, as indicated here by lines drawn perpendicular to the wavefronts. Look at this picture. We have something called ripple tank. Ripple tank is a device used to indicate the shape of waves. Waves, it is the imaginary line on a wave that join all points that are in the same phase. It's usually drawn by joining all the crests. So this is a crest and this is a crest. The imaginary line here is called a wavefront. Also, if we have trough and trough, the imaginary line here joining them is also a wavefront. In a ripple tank, straight wavefronts are perpendicular, line source. The ray is line drawn like this one's, line drawn at right angle to a wavefront, which shows its direction of traveling. The distance between a wavefront to the next wavefront is called wavelength, lambda. And here is the oscillating paddle, which produces the wave. And here, illuminating light source to show the shape of waves on the screen beneath the tank. Let's remember together that we have 4 wave phenomena in all waves. These 4 phenomena are reflection, refraction, diffraction, and interference. Now, let's talk about reflection. Wave reflection is bounding back of a wave off a boundary. Look at this picture here. Yes, it's bouncing. We have 2 examples of reflection, including light reflection in a mirror and sound reflection or echo. You are able to see yourself in a mirror because light rays bouncing off you hit the mirror and reflect back to your eyes. The straight wave before hitting the boundary is called incident wave. After reflection, the wave is called reflected waves. Incident waves and reflected waves. Falling are incident, returning are reflected. If a wave traveling in the air and hits water, the position that the air meets the water would be the boundary. The boundary is any change of medium. If a wave is traveling in the air and it hits water, the position that the air meets the water would be the boundary. At that moment, there would be a reflection and another wave phenomena. Reflection you will see a little later on. This is the incident ray, and this is the reflected ray. Here we have wavefronts. The distance between 2 wavefronts is called lambda, and this is the barrier or the reflecting surface. Now let's talk about light reflection. As we mentioned before, that light is an electromagnetic wave. We said before, electromagnetic means that we have 2 different types of waves. Electric and magnetic fields are perpendicular to each other and perpendicular to the direction of propagation. Look at the blue one here and the orange one. Magnetic field and the electric field both are perpendicular to each other. Let's talk about law of reflection. As we mentioned before that we have incident ray, here we call it incident light ray, and we have a reflecting surface, for instance, it's a mirror. We have first to draw an imaginary line perpendicular to the reflecting surface. This imaginary line is called normal line. So, normal line is perpendicular to the reflecting surface, and there is something called incident angle. Incident angle, or the angle of incidence, it is the angle between the incident ray and the normal line. And also we have reflected angle, or the angle of reflection, which is between the reflected ray and the normal line. The law of reflection here is angle of incidence must equal to angle of reflection. I equals R. Okay? The law of reflection states that when a wave hits a barrier at an angle, the reflection is the same as the angle of incidence. Suppose we have a reflecting surface like a mirror. At first, we have to draw the normal line, which is imaginary line perpendicular to the reflecting surface. And if the incident ray is congruent to the normal line, so the angle of incidence here is No, it's not 90, it's 0. There is no angle between the normal line and the incident ray. As the angle of incidence equals 0, so the reflection must equal 0, so the light ray will reflect on itself as shown in the figure. If we have two reflecting surfaces like this, and we have an incident ray, first we have to draw the normal. The incident ray will make an angle of incidence between the normal and the ray here, this one. In this case, it will be 60. So if I equal 60, so R must equal 60. A single beam from a light is a ray. In the animation here, we are following the reflection of a single ray. Look at this one. Here, it's 60. And the reflected ray from the first reflecting surface will be the incident to the second reflecting surface. To make an angle of incidence here, draw the normal first and make an angle of incidence equals 30 to be reflected also with 30 and falling again to the first reflecting surface. At this point, we have to draw the normal, and the angle of incidence here will be 0 because there is no angle between the normal and the incident ray, which will reflect on itself with an angle of 0 and return back and back again. Now let's figure out the properties and the position of image formed in a plane mirror. If we look into a mirror, we see an image for this object in front of the mirror. For instance, we have the word cat here, and each object will take two incident rays from it. So we have the first incident ray, which will be reflected like this. The second incident ray, which will be reflected like this. Take the extension of the two reflected rays to figure out the position of the image formed behind the mirror, which is imaginary or virtual. So the position of the image formed by a plane mirror will be in front of it, but laterally inverted, or we call it reversed, and on the same distance. So the object here has a distance to the mirror, and the image formed has the same distance from the mirror to the image. And they have the same size. So what kind of image is formed in the plane mirror? They are reversed or laterally inverted. They have the same size as object. It's virtual or imaginary. I mean, cannot be received on a screen. We cannot move behind the mirror to see the image. It's impossible. And this image is erect or upright. So the image will be the same as the object erect. And they have the same distance from the mirror. Between the object and mirror, also between the mirror and the image. The second property of light waves is refraction. Wave refraction is a bending that occurs as light ray enters a new medium. Remember that wave speed will be the same until there is a new medium. Due to a change in speed, the transition into new medium will create a bending. The angle of incidence, which is I, is incoming ray or wave. Here R stands for refraction in the angle of refraction, I and R. And here we have the normal line in refraction diagram is drawn through into the new medium since light travels through. The angle of refraction is measured from the normal line to the refracted ray. As usual, the considered angle is between the ray and the normal. Incident angle between ray and normal, refracted angle between ray and normal. Okay, look at this instance in the first, and it's supposed to move in a straight line, but due to passing between two different mediums, the speed here will change and the refraction will be away or close to the normal. This is according to from high density medium to low density medium or vice versa. Okay. If we have a rectangular glass block as shown, and we need to illustrate how the refraction occurs in it. First, place a rectangular glass block or a perspex in the middle of a page like this on your book and draw around it. Draw a normal. This is the normal line. A third along on the long side. And draw a line with an angle of 20 degrees to this normal to make incident ray. Use the ray box and a single slit, this one, to shine a ray of light along the path you have marked for the incident ray. Mark 2 dots on the path of the refracted ray with a pencil. Join the dots with a ruler to show the path of the refracted ray, and then remove the block and draw the path taken by the ray of light inside the block. Here, this is the incident ray coming from asphalt to sand. Here, it's low density to a higher density medium, so it will reflect close to the normal because it's denser in sand, and then passing from the normal as it moves again to a less density medium. This is the glass block, this is the incident angle, this is the refracted angle at the first side, and the refracted ray here is considered as the incident ray to the second side. Draw the normal, assign the incident angle number 2, and this angle is called emergent angle, which is the second refracted angle. We call it emergent angle. In case of light is passing perpendicular to the block, so it's congruent with the normal here, and there is no angle of incidence. The angle of incidence is 0, so it will pass without any deviation as shown. Look at the figure. Incident ray, incident angle, refracted in a slower medium or in a denser medium, so it will refract close to the normal. And the refractive index here is greater, NR is greater, as we'll study later. Now let's talk about total internal reflection. Light bends away from the normal line when going from slower to faster medium. This is the slower one glass, and the faster one is air. As the angle of incidence increases, so does the angle of refraction. Light no longer refracts into a faster medium after a certain angle called critical angle. Beyond the critical angle, you have total internal reflection and no refraction anymore. Okay? If the angle of incidence is smaller than the critical angle, then the light ray is refracted as usual. If the angle of incidence equal the critical angle, then the light ray is refracted along the boundary like this, and the refraction here will be 90. If the angle of incidence is greater than the critical angle, the total internal reflection occurs, as shown. Look at this figure to figure out what's critical angle. Critical angle is an acute angle in a denser medium which corresponds to refraction in a less density medium, and this refraction will be on the boundary and equals 90. This is the last chance for the light to make refraction. If the angle of incidence becomes greater than the critical angle, the refraction process will be completely converted into reflection, which you call it total internal reflection. Okay? How do optical fibers carry light? Optical fibers and perspex rod do not have to be straight to carry light, and can even carry light around corners by total internal reflection. This is the source of light, and the light here is falling on the side with an angle of incidence which is greater than the critical angle, so total internal reflection occurs, and the reflected ray here will be the incident to the other side, and also is falling with an angle is greater than the critical angle, so reflect by total internal reflection and continues until it reaches to the end of the optical fiber. And optical fibers are used for cable TV and high-speed broadband because glass is transparent to visible light and some infrared. Visible light and short wavelength infrared can carry high rate of data. Now, let's talk about index of refraction. Its symbol is small n. Refractive index or index of refraction is a measure of how much light is refracted or bends in a material. The index of refraction is the ratio of speed of light in a vacuum to speed of light in another medium. C, the speed of light in a vacuum, and V, the speed of light in any another medium. So the ratio between them is refractive index. And the index of refraction is always 1 or greater. The larger the index of refraction, the slower light travels in that medium. The index of refraction has no unit because it's a ratio as shown here. Meter per second over meter per second cancel each other, so there is no measuring unit for any ratio. Okay? The index of refraction is variable in this equation. C equals 3 times 10 power 8 meter per second. For air or vacuum, approximately the same. N is the index of refraction, and V is the velocity of light in another medium. Since C is a constant, which is 3 times 10 power 8 meter per second, the index of refraction equals N equals C over V will always be 3 times 10 power 8 over V, because C is constant, 3 times 10 power 8. Look at this figure. We have incident angle and refracted angle. So to calculate the refractive index, it is the ratio between sine I, incidence angle, and 2 sine R. The sine I over sine R gives us the refractive index until we reach to the critical angle. If we reach to the critical angle, the refraction will be 90. So sine I over sine 90, which equals 1. By making some rearranges, So sine I critical equals 1 over n. Look at this figure. We have a triangle here, and the incident light ray is falling perpendicular to the side with an angle 0 because it's congruent to the normal. So it will pass without any deviation and will be the incident ray on the other side. First, draw the normal and assign the angle of incidence between the incident ray and the normal. So if we know that the refractive index for glass is 1.5, by applying the previous rule, n equals 1 over sine I critical, to find the critical angle for this glass, make rearrangement. So sine I critical equals 1 over n, which is 1.5. Inverse sine I to get I critical equals 41.8 degrees. And the incident angle in this case will be greater than critical angle. So total internal reflection occurs here because the angle of incidence is 45 and the critical angle is 41.8. So the angle of incidence is greater than the critical angle. So total internal reflection occurs. And the angle of reflection will be 45 also, which is equal to the angle of incidence. The incident angle here will be 0 and pass without any deviation because it's 0 incident angle. So the reflection here occurred by 90 degrees here, which is used in optical instruments, periscopes, in submarines. Here, if we have the incident ray on this side, it passes without any deviation because the angle of incidence is 0 and falls to the other side with an angle of incidence greater than the critical angle. Draw the normal and make the angle of incidence which is greater than the critical angle. So total internal reflection occurs. So it will reflect like this as the previous. The n here, the refractive index is 1.5, making rearrange. So I equals 41.8. The incident angle is greater than the critical angle. Total internal reflection occurs. And falling on the other side with an angle of 45, which is also greater than the critical angle, total internal reflection occurs. And falling to the first side with an angle of incidence 0, pass without deviation. In this case, we're able to rotate the light with an angle of 180 degrees, which is used in binoculars. Snell's law of refraction, here we are. Snell's law can be used to mathematically calculate the angle of bend or index of refraction on the incident side or refracted side when light travels between two mediums. I is the incident angle at the first side where light starts, and R is the refracted angle on the second side where light goes. Medium 1 refractive index has N1 and medium 2 has a refractive index N2. So according to Snell's law says that N1 sine I, which is theta 1, equals N2 sine R, which is theta 2. We can write it like this or in the form of fractions. N1 over N2 equals sine theta 2 over sine theta 1. Or we can say N12 equals sine R over sine I.